welcome back to this channel. For today's video, we'll discuss about topic 7.2 molecular shape, part 2. In this video, it's still related to your VSEPR theory that we have discussed in the part 1. But we will no longer focus on the basic geometry, we'll focus on the molecular geometry when there is a lone pair at your central atom. First and foremost, just to recall what is actually VSEPR theory, is your valence shell electron pair repulsion theory. It's talking about all the electron pair in your Lewis structure will tend to repel each other and move as far as possible to minimize the repulsion. We have 3 types of repulsion. They are lone pair repulsion, lone pair bonding pair repulsion, and bonding pair repulsion. In the lone pair repulsion, you need to have minimum 2 lone pair in your structure. Alright, so these 2 lone pair will repel each other and tend to change the molecular shape. For the lone pair bonding pair repulsion is when you have 1 lone pair and also some bonding pair. So you have your lone pair and a bonding over here, therefore you have a repulsion between them, and that is your lone pair bonding pair repulsion. And last but not least, when you only have bonding, you will still have repulsion where the bond and the bond will repel each other. And obviously, the lone pair repulsion is the strongest among these 3. And your bonding pair repulsion is the weakest repulsion among these 3. We have 5 basic molecular geometry that we have discussed in your previous video, which is your linear, trigonal planar, tetrahedral, and trigonal bipyramidal. Last but not least, octahedral. If you realize in all these 5 basic molecular geometry, there is no lone pair at your central atom. In the other words, in this basic molecular geometry, you will only have bonding pair repulsion because there is no lone pair at the central atom. But what happens when you have lone pair at the central atom? How will this affect the molecular shape? Let's see. Let's start with the linear. This is some general information of linear. You know that it's an AX2, something like this. And then the number of electron pair is 2 bonding pair plus 0 lone pair. Bear that in mind, the formula of electron pair is the number of bonding pair plus lone pair, where in the number of bonding pair, you only need the count of sigma. So, for the linear, you have 2 bonding pair plus no lone pair. There is no lone pair. Therefore, the electron pair geometry will be linear, or in the other words, the basic geometry is linear. And the molecular geometry will also be linear because there is no lone pair in the central atom. The bond angle is 180 degrees. Let's look at a simple example. I have a BH2 over here. The Lewis structure is as given. We have learned how to draw Lewis structure in your 7.1. If you don't know why the structure look like this, please go and watch the video on how to draw Lewis structure. When you have the Lewis structure already, the first thing that we do is to calculate the number of electron pair. The formula to calculate the number of electron pair is bonding pair that we will need the count of sigma plus lone pair. So the bonding pair I have over here is 2. The lone pair I have around the central atom is 0. Bear that in mind, we only look for the central atom. Therefore, the number of electron pair total is 2. From the number of electron pair, we know that the electron pair geometry, or we call basic geometry, will equals to linear due to the electron pair is 2. And we know that linear looks something like this. That is how a linear look like. And what would be the molecular geometry? Molecular geometry will be affected or will change if there is a lone pair in your central atom. But if you look at your central atom, there is no lone pair. The lone pair is 0. Therefore, there is no lone pair repulsion, or there is no lone pair bonding pair repulsion. Therefore, the molecular geometry will remain linear. When the molecular geometry remain linear over here, your Lewis structure needs to be redrawn in the shape of linear if you haven't drawn it correctly. If you have, then it's fine. So your molecular geometry linear will look something like this. Therefore, your bond angle over here will be 180 degrees because the molecular geometry is linear. So for this linear, there is no lone pair at the central atom. Therefore, the basic geometry will equals to the molecular geometry. But what happens if there is lone pair? Let's look at trigonal planar. Here is some basic information of trigonal planar, where you know that the general formula is AX3. We have 3 bonding pair plus 0 lone pair, where the electron pair geometry will be trigonal planar, molecular geometry will be trigonal planar because there is no lone pair. No lone pair means your central atom will be holding your X in the shape of trigonal planar. Therefore, the bond angle will be 120. And you will only have bonding pair, repulsion. What happens if you're having a lone pair? If you look at it, my general formula changed from AX3 to become AX2E. The E over here represents lone pair. So I have one lone pair over here. In the other words, your AX will be something like this. AX2, one of the bond is replaced and substituted by lone pair. So, your electron pair geometry will still be trigonal planar because the total number of electron pair is still 3. 2 plus 1 is still 3. So, the basic geometry is still trigonal planar. But, due to one of the bonding is substituted by the lone pair, therefore, the molecular geometry changed from trigonal planar to V shape. That is your V shape. Can you see your V shape? Alright. And the bond angle changed. The bond angle will no longer be 120, but the bond angle will be smaller than 120. Why? Because you have the presence of lone pair, bonding pair, repulsion. Where the lone pair, bonding pair, repulsion is stronger than the bonding pair, repulsion. So the lone pair will press the bond go down. Therefore, the bond angle from 120 will be less than 120. Make sense? Let's see some example for both of this. The first example for trigonal planar is your BCl3. So the Lewis structure of BCl3 looks something like this, from your total valence electron and all that. Okay, that is my Lewis structure. And when you have the Lewis structure already, the first step is to calculate the number of electron pair. The formula is bonding pair, where we take count of sigma, plus lone pair of the central atom. That is my central atom. The sigma bond I have over there is 3, and the lone pair I have over there is 0. There is no lone pair in your boron. So the number of electron pair is 3. When the number of electron pair is 3, the basic geometry or the electron pair geometry will equals to trigonal planar. And we know that trigonal planar looks something like this. And since there is no lone pair, none of the bond will be replaced by lone pair. Therefore, the molecular geometry will also remain unchanged and maintained as a trigonal planar. And since we know that the molecular geometry is trigonal planar, you need to redraw your Lewis structure in the correct shape. So the correct shape of your trigonal planar will be in the triangle. And that's how your trigonal planar look like. Why the basic shape and the molecular geometry remain the same? Simple, because there is no lone pair. The only repulsion that you have is bonding pair, repulsion. So the basic geometry and the molecular geometry remain the same. And that's why your bond angle will also remain 120 degrees. Let's look at another example, NO2-. And the Lewis structure given is as this. Learn on how to draw the Lewis structure, okay? Make sure you know how to draw the Lewis structure on your own. And the first thing when you have the Lewis structure is the number of electron pair, of course, is your bonding pair that we take count of sigma plus lone pair. And the sigma over here is only 2. I have only 2 sigma. 1, this is a pi, so we don't take count of the pi, we only take count of the sigma. Lone pair, how many lone pair the central atom having? We have 1 lone pair, so plus 1. So your number of electron pair remain 3. And when the number of electron pair is 3, your electron pair geometry or your basic geometry will be trigonal planar. And everybody knows that trigonal planar looks something like this. But in this structure, there is 1 lone pair. So what happened is we only have 2 bonding pair and 1 lone pair. So in this 3 bonding, we need to substitute one of the bonding with lone pair. Therefore, your molecular geometry will change from trigonal planar to become V-shaped. Why? Due to the presence of lone pair, therefore you have lone pair, bonding pair, repulsion. When you have your lone pair, bonding pair, repulsion, the molecular geometry change from trigonal planar to V-shape. And therefore, this Lewis structure is now wrong because your NO2 minus is not in the shape of linear. It should be in the V shape. So you need to redraw your NO2 in the V shape. Make sure you have the charge and make sure you bring in all your lone pair that you have as above. And don't forget the lone pair at the nitrogen central atom. Due to the presence of this lone pair, your geometry changing from trigonal planar to V shape. And the bond angle will also change because the bond angle will now be less than 120 degrees. Due to the presence of your lone pair, your bonding angle will get smaller. Make sense? Simple. First and foremost, we still need to get the correct Lewis structure first. So make sure you know how to draw your Lewis structure correctly. Next, let's look at tetrahedral. How would the molecular geometry change when you have the presence of lone pair at central atom? Let's see. The basic information of your tetrahedral, your general formula AX4, the number of bonding pair is 4 bonding pair and 0 lone pair. So the electron pair geometry is tetrahedral. The molecular geometry also is tetrahedral because there is no lone pair. The bond angle is 109.5. And what would happen if there is 1 lone pair? When the number of bonding pair change from 3 bonding pair plus 1 lone pair, your geometry will change from tetrahedral to trigonal pyramidal. Let's see. Your tetrahedral looks something like this. And right now, we don't have 4 bonding. We only have 3 bonding plus 1 lone pair. So one of the bond need to replace with lone pair. Therefore, the shape obviously change. It will no longer be tetrahedral, but it will be trigonal pyramidal. And due to the presence of this lone pair, the lone pair repulsion will cause the bond angle to get smaller. And that's why the bond angle will be less than 109.5, which is approximately 107 degrees. And this is all because in here, we have lone pair, bonding pair, repulsion. And what would happen when you have 2 lone pair? Over here, you can see at the number of electron pairs, you have 2 bonding plus 2 lone pair. So what will happen to the tetrahedral? Your tetrahedral is now having 2 bonding and 2 lone pair. So 2 of the bonding need to substitute with a lone pair. So what left? Can you see the V shape? Again, V shape produced. So your basic geometry or your electron pair geometry will change from tetrahedral to a V shape because 2 bonding pair is replaced by 2 lone pair. That is your V shape. And the bond angle will be less than 109.5 because we started off as a tetrahedral. The original bond angle is 109.5. So when you have 2 lone pair, the repulsion will be even stronger. So the bond will be smaller than 109.5, which will be approximately 104.5 degree. Why the bond angle over here is 107 degree, over here is 104.5 degree? Simple. If you are having 1 lone pair, you will have lone pair, bonding pair, repulsion. But when you have 2 lone pair, guys, you will have lone pair, repulsion. And we know that lone pair, repulsion is stronger. When the lone pair, repulsion is stronger, it will be able to push the bond to be even closer to each other. That's why the bond angle will be even smaller. Make sense? Alright, simple. Let's look at some example. I have CH4. The Lewis structure given as this. So from the Lewis structure, you need to calculate the number of electron pair, starting with the bonding pair that we take count of sigma plus lone pair. So your bonding pair over here is 4, no lone pair at the central atom, 0. So number of electron pair is 4. And your electron pair geometry will be tetrahedral. And your tetrahedral will look something like this. And obviously, guys, there is no lone pair. So simple question. There is only bonding pair. The number of bonds will remain unchanged. Therefore, the molecular geometry will remain tetrahedral. In the other words, the electron pair will be equal to the molecular geometry if there is no lone pair at central atom. Therefore, the electron pair geometry, the basic geometry, will be equals to the molecular geometry. And your correct Lewis structure should look something like this, in the shape of tetrahedral. And the bond angle of this tetrahedral with no lone pair, the bond angle will remain 109.5 degree. Agree? Okay. What happens if you have a lone pair? The next example, ammonia. And the Lewis structure of ammonia given is this. And pay attention to your central atom. There is a lone pair. So first step, still the same. Calculate the number of electron pair. Still the same formula that we use. And over here, the bonding pair is 3. Sigma, sigma, sigma. And your lone pair is 1. 1 lone pair. And the number of electron pairs total will be 4. From the total number of electron pair, your electron pair geometry will still be tetrahedral. And your tetrahedral should look something like this. But right now, we only have 3 bonding pair and 1 lone pair. So one of the bond need to be substituted by a lone pair. And therefore, the molecular geometry will change to trigonal pyramidal. Can you see what left above? You have a pyramid. Okay, it's kind of like a pyramid. So you have a trigonal pyramidal over here. And your NH3 need to be redrawn into the correct shape. And you can draw it simply like this. Your N as your center. You have your H open up like your chicken leg. And then don't forget the lone pair. The lone pair is the reason why it changed from your tetrahedral to your trigonal pyramidal. And your bond angle will change from 109.5 to less than 109.5 degree. That is because in here, you will have the presence of lone pair, bonding pair, repulsion. And this repulsion will cause the bond to get closer, and therefore, the bond angle becomes smaller. Next, let's look into H2O, a very simple molecule that you always come across. The Lewis structure of water molecule as given. And what do we need to do first to determine the molecular geometry? First and foremost, number of electron pair. Still the same formula. And look at your central atom right now. Your central atom having 2 bonding pair and also 2 lone pair. So your total number of electron pair also remain 4. Therefore, the electron pair geometry or your basic geometry will remain the same. When the number of electron pair is 4, the basic geometry will remain tetrahedral. You can sketch out your tetrahedral first. Tetrahedral looks something like this. But you have 2 lone pair over here. So 2 of the bonding need to be replaced with a lone pair. 2 of the bonding need to replace with a lone pair. And what is the shape formed right now? Can you see the V shape? The molecular geometry of water will become a V shape. Why? Presence of 2 lone pairs at your central atom. And due to the presence of these 2 lone pairs, you will then have lone pair, repulsion. And that will cause your bond angle to be smaller than 109.5 or approximately 104.5 degree. It will be smaller than your trigonal pyramidal. And before you end, we need to redraw your water in the correct molecular geometry. Your water should be something like this. The V shape, O, and you have 2 lone pair. Bear that in mind, the lone pair must be at the top. Can you see over here? The lone pair must be at the top. Then you will have a V shape over here. So make sure you redraw your Lewis structure to the correct molecular geometry before you end your question. It's very important to get your Lewis structure in the correct molecular geometry. Next, we'll look into trigonal bipyramidal. We know that your trigonal bipyramidal looks something like this. That is how your trigonal bipyramidal look like. The basic information for trigonal bipyramidal, general formula AX5, the number of bonding pair is 5. The total number of bonding pair must be 5 for the basic trigonal pyramidal. The electron pair geometry will be equals to the molecular geometry because there is no lone pair. And the bond angle for trigonal bipyramidal, that is 120 and 90. I hope you remember that is your 90, that is your 120. But what happens when you have a lone pair? When you have a lone pair, one of the bonding pair is substituted by the lone pair. So your trigonal bipyramidal change to seesaw. What is actually seesaw and why the bond angle is less than 120 and less than 90? Don't worry, we'll look into the example later on. The next is when your trigonal bipyramidal having two lone pair. So when you have two lone pair, the trigonal bipyramidal change to T shape. And the bond angle will be less than 90. Again, why? Last but not least, when the trigonal pyramidal is having three lone pair at the central atom, the trigonal pyramidal will change to linear. Why suddenly there is linear in your trigonal bipyramidal? Because you have three lone pair. And the bond angle, since it's a linear, therefore the bond angle will be 180. Don't worry, we'll go through example one by one. The first example I have is PF5 and the Lewis structure as given. And the first step, of course, the number of electron pair, bonding pair sigma plus lone pair. So the bonding pair sigma is 5, 0 lone pair in this case, number of electron pair is 5. And the electron pair geometry will be trigonal bipyramidal. And the trigonal bipyramidal looks something like this. And since there is no lone pair in your central atom, therefore, the electron pair geometry must equal to the molecular geometry since there is no lone pair in your central atom. And make sure you redraw your Lewis structure again in the correct shape. So that is a correct shape. This is fine. I just want to show you another way of drawing. You can have your trigonal bipyramidal like this. And it's still trigonal bipyramidal. Both over here are correct drawing for trigonal bipyramidal, anyone that you are comfortable with. And since there is no lone pair, so the bond angle will also remain 90 degree and also 120 degree for trigonal bipyramidal because there is no lone pair. But what happens when there is one lone pair? The next example we have SF4. And look at your central atom. Your central atom right now holding a lone pair. So what would be the number of electron pair? Number of electron pair will be bonding pair plus lone pair. So your bonding pair over here is 4 sigma plus 1 lone pair. Number of electron pair remain the same, 5. Therefore, your electron pair geometry will remain trigonal bipyramidal. And we know that a trigonal bipyramidal standard looks something like this. But right now, one of the bonding need to be substituted with the lone pair because you only have 4 bond and 1 lone pair. So which bond are we going to remove? According to VSEPR theory, we are going to minimize the repulsion. We have 2 bond angle, we have a 90 degree and we have a 120 degree. So 90 degree and also 120 degree, which one will give you minimum repulsion? Of course, the 120 degree. Because 120 degree, they are far away from each other. So, we will replace one of the bond in this triangle with a lone pair. Any one of this triangle with a lone pair. Let's say I replace this bond with a lone pair. So, your lone pair will be located over here. And what shape are you getting? You'll be getting your molecular geometry seesaw. Can you see the seesaw over here? That is your seesaw. Okay? And therefore, you need to redraw your Lewis structure in the correct molecular geometry. We need to redraw this in the seesaw shape. So you are going to have your S. Seesaw will be drawn like this. Can you see the seesaw? So you put in your F. And the most important is the position of this lone pair. The lone pair must be at the top of here. Then you will have a seesaw. And don't forget the rest of the lone pair of fluorine. And that is how your seesaw look like. And this will be the correct Lewis structure because they are in the correct molecular geometry. And the bond angle will change. Why the bond angle will change? Because you will have lone pair, bonding pair, repulsion. When you have the lone pair, bonding pair, repulsion, this lone pair will tend to push the bond angle to be closer to each other. Therefore, the bond angle will be less than 90 degrees and also less than 120 degrees due to the repulsion of the lone pair at the central atom. So the bond angle become smaller. Make sense? And that is when your central atom having one lone pair. And what would happen when your central atom having two lone pair? According to this Lewis structure, your ClF3 will look something like this. And your Cl holding two lone pair, guys. First step is still the number of electron pair. We need to know the basic geometry before the molecular geometry by calculating the number of electron pair. So the number of electron pair, bonding pair sigma, plus lone pair of your central atom. So your bonding pair over here, 3 sigma plus 2 lone pair, 1, 2. And the total number of electron pair is 5. From the total number of electron pair, you will know the electron pair geometry, which is also we call basic geometry. The basic geometry that you have over here when it's 5, obviously, trigonal bipyramidal. And your trigonal bipyramidal will look something like this. But right now, we don't have 5 bonding. We only have 3 bond, but with 2 lone pair. So 2 of the bond need to be substituted by the lone pair. Like we have discussed just now in the trigonal bipyramidal, we have 2 bond angle. We have 90 degree, we have 120 degree. So to put in the lone pair that have a very high repulsion, they will choose the one with the highest angle so that they can stay far away from each other and minimize the repulsion. So between the 90 degree and the 120 degree, so which one will we choose? The 120 degree. So we will replace 2 bonding in the 120 degree with a lone pair. Lone pair, lone pair. That's why you have 2 lone pair with 3 bonding left. And what shape can you see over here? Your T shape. Therefore, your molecular geometry will be a T shape. Alright? And we need to redraw this Lewis structure. And why I say this Lewis structure is wrong. Although it's already in the T shape, because the position of your lone pair over here is wrong. Your lone pair must be together at the top. Therefore, the correct Lewis structure in the T shape should be something like this. The T shape. And the most important is the position of the lone pair. The lone pair needs to be here. There's no other place. The lone pair needs to be here. And this will be the correct Lewis structure with the correct arrangement of the lone pair. Bear that in mind, we are not only looking at the shape other than the T shape that you have drawn. The location of the lone pair is very, very important because lone pair is the one that's changing your geometry right now. And your bond angle when it's a T shape, there will be no longer 120 degree. There will be only 90 degree over here. Therefore, the bond angle for T shape will be less than 90 degree. The bond angle get even smaller because you have a lone pair repulsion. And this lone pair repulsion is very strong. So the bond angle will be smaller and smaller. Next, what happens when you have 3 lone pair at the central atom for XeF2? Let's check whether they are still trigonal bipyramidal or not by calculating the number of electron pair. So you have your bonding pair, sigma plus lone pair. Your bonding pair sigma is 2. You have 3 lone pair over here. 1, 2, 3. So the total number of electron pair remain 5. When the total number of electron pair remain 5, the electron pair geometry will remain trigonal bipyramidal. And again, guys, trigonal bipyramidal shall look something like this. But unfortunately, we only have 2 bonding, but we have 3 lone pair. So what do we need to do is, we need to substitute 3 bonding with 3 lone pair. Over here, like we have discussed many times just now, I have a 90 degree and I have a 120 degree for this triangle. So to put in the lone pair, we will always choose the furthest away, the one that we can move far away from each other. So the one that can move far away from each other is the triangle in the center, having a bond angle of 120. So this 3 bonding will be substituted by the 3 lone pair. And what shape do you see over here? You see a linear. So you see a linear over here. And that's why the molecular geometry will be linear. When the molecular geometry is linear, your Lewis structure needs to redraw, and the position of the lone pair is very important. This is the correct Lewis structure because it's already linear, and you can see that your lone pair is located in the triangle shape at the center. You can draw it in another way. You can also draw it like this. And the position of your lone pair, can you see? So your position of your lone pair will be 1, 2, 3. That is how your trigonal bipyramidal changed to become linear due to the presence of 3 lone pair at the central atom. And this will also be the correct drawing of XEF2. The bond angle will be 180 degree. So the question is, why there is lone pair repulsion, but the bond angle remain 180? Because the location of the lone pair in a triangle like that, so the repulsion of the lone pair will cancel off each other. When they cancel off each other, this will remain as a linear 180 degree. Therefore, your bond angle remain 180 degree linear. Next, and also last but not least, let's look into octahedral. The basic information about octahedral, the general formula AX6, you have 6 bonding with no lone pair, and the electron pair geometry is octahedral, where octahedral looks something like this. And the molecular geometry will remain octahedral because there is no lone pair. The bond angle is 90 degree because the only repulsion that you have is bonding pair repulsion. What would happen when you have a lone pair? When you have a lone pair, your octahedral are no longer holding 6 bonding. You will be only holding 5 bonding with 1 lone pair. And since all the angle in your octahedral is 90, so you can substitute any one with the lone pair. So let's say when I substitute this with my lone pair, I will then form a square pyramidal. So your square pyramidal will look something like this, with a lone pair here. And the bond angle will be less than 90, and the reason is the same. Why is less than 90? Because you have lone pair, bonding pair, repulsion. So the bond angle become smaller. Last but not least, what would happen when you have 2 lone pair? When you have 2 lone pair, your octahedral will have 2 bonds to be substituted with the lone pair. So let's say if I choose the top and bottom and substitute with the lone pair. And what will I form? I will form a square planar. I will change to a square planar. And in your square planar, you will have lone pair at the top and lone pair at the bottom. And the bond angle will remain 90. We'll look into why later on in the example. The first example that we have on the screen, SF6, and the Lewis structure as given. So the first step is to calculate the number of electron pair, your bonding pair, sigma plus lone pair. Your bonding pair is 6 plus 0 lone pair, 6 number of electron pair. Therefore, the electron pair geometry will be octahedral. And since it's an octahedral, the shape should look something like this. And since there is no lone pair, therefore, your molecular geometry will also remain as octahedral. And your Lewis structure is already in the correct octahedral. You can see that. That is your octahedral. Therefore, you do not need to redraw your Lewis structure. And the bond angle for the octahedral over here will be 90 degree. Reason? Because you only have bonding pair, repulsion. So it will remain 90 degree. And again, kind reminder, your electron pair geometry will be equal to the molecular geometry if there is no lone pair at the central atom. Remember that, okay? So what happens if you have lone pair? Look at your structure over here. You have your BrF5 and the Lewis structure given is having a lone pair in your central atom. So what would be the number of electron pair? Bonding pair plus lone pair. Your bonding pair right now is 5 with 5 sigma plus 1 lone pair in the central. Therefore, the number of electron pair is 6. And since the number of electron pair is 6, your electron pair geometry will be octahedral. And your octahedral should look something like this. But we only have 5 bonding. You only have 5 bonds. So one of the bond need to substitute with a lone pair. And you can substitute any bond. It's the same because all the angle in your octahedral are 90 degree. So I can substitute anyone. I choose the bottom one this round. So you substitute this with a lone pair. And what are you forming? You are actually forming a square pyramidal. Can you see the pyramid? Alright, you're actually forming a square pyramidal. So your molecular geometry will be a square pyramidal. And you need to redraw your BF5 Lewis structure in the shape of square pyramidal. How should your square pyramidal look like in a 2D? Simple. Put in your central atom. I have my Br. Just follow what you have above here. So you have a bond up there. You have a square in the center. And most important, you have a lone pair down here. And then you put in all your F as a terminal atom. And this is how a square pyramidal should look like for BrF5. Bear that in mind, the position of your lone pair is very important when you are drawing the correct molecular geometry. Okay? And what would be the bond angle? The bond angle will be less than 90 degree. Because the presence of lone pair, the lone pair will have repulsion, strong repulsion, and it will push the bond closer to each other. That's why the bond angle becomes less than 90 due to the presence of lone pair, bonding pair, repulsion. Okay? Last but not least, what would happen when you have 2 lone pair at the central atom? So your number of electron pair over here will be bonding plus lone pair. And your bonding is 4 and your lone pair is 2. So your number of electron pair remains 6. And from the number of electron pair is 6, therefore you know that your electron pair geometry or your basic geometry will be octahedral. And your octahedral should look something like this, with 6 bonding for a basic geometry. But unfortunately, we don't have 6 bonding. We only have 4 bonding over here and we have 2 lone pair. So 2 of the bonding need to substituted by the lone pair. And the first one, you can choose anyone. So I choose the top one for this round. So I choose this for the lone pair, for the first lone pair. And the second lone pair should go into where? The second lone pair, you need to choose the one that furthest away from the first lone pair. So if the first lone pair, you are putting it here, the second lone pair must be the 180 degree away from it, the one that far away from it. So the opposite position. This is where you put the second lone pair. Bear that in mind, the second lone pair must be always the furthest away position as possible to minimize the repulsion. So you must choose the opposite direction like this. After you substitute the 2 bonding with lone pair, you realize that you have a square left. And that is how your square planar look like. So your molecular geometry will then be square planar. And how should your square planar look like? Just like above. So you have your XE in the center. And then you have a square for your F. And most important, where is the lone pair? You can refer to the top drawing. You can see that your lone pair is at the top and at the bottom for the square planar. So don't do mistake for the position of the lone pair. The position of the lone pair is also very important to determine the molecular geometry. And that is how your square planar look like. Okay? And since it's a square planar, it will be sitting on the plane like that. So what would be the bond angle? The bond angle will remain 90 degrees. Why? Even though there is a lone pair repulsion, but the lone pair repulsion cancel off each other. Why? Because the lone pair is at the top, the lone pair is at the bottom. When the lone pair at the top push it downward, the lone pair at the bottom will push it upward. So one pushing it downward, one pushing it upward. Therefore, they will be equal. The lone pair repulsion will cancel off each other. That's why the bond angle remain 90 degrees. Therefore, position of the lone pair is very, very important. And that's it for this video. I hope by now you understand how to find the molecular geometry when there is lone pair at your central atom. Bear that in mind, we will still depend on a very correct Lewis structure. And from the Lewis structure, we will calculate the number of electron pair. From the electron pair, we will see what is your electron pair geometry or what is your basic geometry. And from the basic geometry, you will think which bonding to replace with lone pair. And from there, you will get your molecular geometry. And from the molecular geometry, you can identify the bond angle. Alright? Simple. So that's it for this video. I hope the video can help you to improve your understanding on this molecular shape. If it does, do give me a like for this video and do subscribe to my channel for more videos. I'll see you in the next video and thank you.